good enough. So we have a flag somewhere here that we'll get to in a moment, what this flag exactly represents. And it has so that's the structure of each node of the Y. And it can contain one Boolean flag, 0 or 1, maybe pointer to other information if you have. And it contains 4 pointers, the addresses of at most 4 other nodes. Address meaning where is this other node, V1, where this other node, V1, starts. Again, A will point to where this other node starts, the first byte of this other node. But the first cell, I'll think about it as a cell that corresponds to the letter A, next the letter B, the letter C, and the letter D. That's how I understand what each cell represents. Okay, and what is this flag exactly? You don't know yet, but the rule is each node corresponds to a word W, and if that we'll see how we understand what word each node represents, and we'll understand that W is a word in the dictionary. W is a student in our class, if and only if the flag that corresponds to W is on. Quick example. Here, S equals A, B, and DBB. So one word that is stored in my database, I have a student whose name is A, I have a student whose name is B, I have a student whose name is DBB. And the try that corresponds to it will be this one, where I'll understand this. No, this pointer, this arrow, as corresponds to the letter A. Why A? Because it's coming from the first cell. The label that I'm adding to an edge, the label that I give to an edge corresponds to the label that I give to an edge corresponds to the cell from which this edge exits, this edge leaves. If it leaves the cell of B, then I'll imagine that there is a label associated with this. Imagine, I mean, I don't really need to store it anywhere. I just, when I'm trying to understand for a node what this node represents, at this moment I'll ask what is the path that leads to this node, and that's the point that I'm doing this mental trick of thinking what's the label of the edge. Okay, so I have the node V1 in my case. Just use real estate a bit better. I'll have the node V1. I will have the node V2. And I'll have the node, in this case, V3. Well, what does this first node, V1, represent? As I said, every node represents a word. Again, every node represents a word. What is this word that V1 represents? Or let's restart. What is a word that W represents, that the root represents? I'm still sleeping. Well, the root represents the word. Root said the word that is associated with the root is empty. No characters. The empty is string. Is visible? Yes, it's visible in the other color. Okay. In general, to understand what a node represents, what is a word that a node represents, I need to concatenate all the labels, concatenate, put one after the other, all the labels, all the path that leads to this node. So this edge, what it's labeled, we said it's coming from A, so we imagine that it corresponds to the letter A, which means that V1 corresponds to the word A, which might or might not be a word in my alphabet. I'll have to look at the flag to know. A word in my dictionary, sorry. The letter, the word A might or might not be the name of a student in my class. V2 corresponds to the word which is B. V3 in this case, note that the edge to it comes from D, so I think about it as label D, and it corresponds to the word, obviously. W, the word that corresponds to it is D. Now, from V3, this guy, I have an arrow coming from the second cell. Second cell corresponds to what? Second cell corresponds to A, B, C, D, B. Why B is the second cell. So this first cell is A, next cell is B, next cell is C, next cell is D. This cell corresponds to B just because it's the second one. That's how I know that it corresponds to B. And it points to another node. And what is the label that I imagine that this edge carries? How do I know which letter this edge carries? Well, it's the letters that it's coming from. That's the rule. The label of an edge is a label determined by from which cell it is coming. It's coming from B, so I'll imagine it that there is B associated with this edge, which means that to which word this node represents? Help? What is a word that this node represents?
AB.
D followed by B. Absolutely. The first one comes from D, so I imagine that the edge is D. The second one comes from B, so I imagine that the label of the edge is B. I'll concatenate D followed by B, so the word that is written right here is the word D, B. I don't need to store it in the word itself. I don't need to store it on the node itself. The node just know about its array and its 4 pointers, 4 addresses plus its flag. But I don't need to store the word DB right here. How do I know that it corresponds to DB? Because if at any point I'll get to this node, I must get to it through the tree. A tree, we know that there is a single path from the root to every node. I'm just looking at what is the path that I followed to reach to this node. And from this node, in my example, before that, what happened to the cell corresponds to D in this case. It doesn't point to anything, so I'll imagine that it points, some people like to denote it as it points to the ground, a symbol taken from electrical engineering, electric circuit. Some people will say we are putting a null pointer in this part. Null is just a constant, in C usually it's 0, but you are using it to denote I point to nothing. So if I don't really point to an address, then this contains null, this contains null, this contains null, this contains null, and so on. Everything that is not specified. Okay, so I'm at this node corresponds to DB, and from the B node over here, and from the B node, I have a pointer to yet another node. What is the label of this edge? Label of this edge is coming from the cell B. That's why I'll denote it the edge as B. And this node corresponds to, therefore, D followed by B followed by B. Then the word over here, is D, B, B. Okay, and now let me remind you what the flags are saying. Every node that you see here corresponds to some word, but this word might be a name of a student in my class, or might be a name of a student, but that is not in my class, not in the dictionary. How do I know for a node if it's in the dictionary or not? That's where I'm using the flag. 0 or 1 at the end. 1 at the end, 1 as a flag, implies this word is in my alphabet. This word is in S, in my list of students, in my dictionary. So node V1 corresponds to the word A, don't confuse, not the letter A, is 1, because A is a word A. As I said, S, the list of words, A is one of the students. 1, because B is one of the students, and D, B, B is also 1, because it's one of my students. That corresponds to the letter DBB, to the word DBB. What is the flag over here? Yep, the flag over here? 0, because DB at the moment is not in my class, not in S. The same goes for this guy over here. So now you all imagine how I'm doing a find operation in the tree. You're performing find of DB, and what will I do? I look at the first character in this word. I look at the root of the tree, and I'll ask, is there an edge that's coming for the cell that corresponds to D? Let me make it a bit bigger for the camera. Find DB. Look at the first letter. Start from the root of the tree. The first letter is D. Is there a pointer coming from the cell of D, or is a cell of D points to null? Well, it doesn't point to null. There is a real pointer coming from it. So let's follow this pointer and move to the second letter. Now I'm checking this node, and I'm asking if there is an edge corresponds to B. Yes, there is an edge corresponds to B. So I'll follow it, and I reached in C, if you like it, there is a \0 that I just discovered to denote the end of the string when I reach this node. Otherwise, just abstract it as I reach to the end of the node, and when I reach the end of the node, I'm visiting this. When I'm reaching the end of the string, which node am I looking at? P, the node that I'm looking at right now, is this guy. In the tree, in the slide, it will be this guy. And I know that there is no more words because, if you like, C, I reach the \0 that denote the end of a string. So what do I check? Or what is my answer? My answer is this node corresponds to a letter in the alphabet. It corresponds to this node corresponds to a word in my dictionary. To know it, I just need to look at the flag. The flag here is 0, so the answer is no. It is a word, there is a node for it, but it's not in my alphabet. Fair enough? So instead, actually, in the code itself, if you look at it, in the code itself, all you are returning is, instead of checking yes or no, you are just returning the flag of the node P that you are looking at. And that will tell you, yes, there is somebody or not. Sometimes, like in the final or in the final or in the homework, I'll ask you, tell me how many words start with DB. How many words in my dictionary start with DB? And to answer it similarly to the size fields that we used in the skip list, to know how many words start with DB, I'll keep a counter with each word that will tell me how many children does it have, how many descendants actually does it have. So you can contain various other information. Just curiosity, it's not relevant for this course too much, but to know how your C works. How many of you understand this syntax? P dot A at the address W of I. W is a string I'm trying to find, so it's a I is the index that I'm looking at right now. I equals 0 is the first node, is the first letter, I equal 1, the second letter of W, but W of I minus A in this way. Do you understand what it means? Both of you understand that what is written here in the parentheses is just the numbers 0 if W of I is A, 1 if W of I is B, because it's B minus A in ASCII. It's coming next to each other. If W of I is C, then you're getting 2 over here, which means I'm looking at the third cell and this area. Okay, let's do another find. So everybody understood why the find of DB will return 0? Because you will end at this node. You look at the flag of this node, and the flag of this node is containing the flag of this node is 0. It's not a, it's a no, it's a word in my language, but it's not the name of somebody in the dictionary. If I do the same find, but with DBB, I'll get to this node and return the flag over here. Next, let's do find of DA. Find of DA starts the same way. Look at the first letter, go to the root. First letter is D. D minus ASCII value of A is 3, so look at the third cell of the root. It's not null, so we can follow it to the next node, and now we are checking the A. Look at this node, but ask if there is a, what happened to the cell, at cell W of now 2, which W of 1, which in this word will be, at this word it will be A minus A is 0, so I'm looking at this array at address 0 of this node, and I'm asking, is this cell points to null, or does it point to a different word? In our case, it points to null, so we declare that we cannot follow this route anymore, and we are declaring that that it points to null, so we are returning false. This word is not in our language. Summarize to not summarize. So the find operation, how much time does it take? How much time the find operation takes? If every operation takes constant time, then it's constant time per letters. So if you have k letters in W, then the whole operation takes theta of k. Theta you remember, not more than k, not less than k. 1 per every letter of the word. Well, +1 for the backslash 0, etc. So it satisfies my first requirement about the running time. How do I insert a word W? I'm performing find of this word. If I find W and it's actually in the dictionary, then I don't reinsert it. I don't double insert it, obviously. If during the find operation I didn't find it, the find fails because I ran into null, then I'm creating new nodes, creating new node or new nodes depending on what I need to do. That is, let's insert DAA. I want to insert DAA. Insert DAA, how will it work? Start from the root. Somebody wants to take over? Insert DAA. Help?
We go from the D, go all the way to the next node. Then
from the root, follow the label of D. It's not null, so you can follow it to the next node. And that took care of the first letter of the DAA. So now you're thinking about the next letter of this word, which is A. Please go on.
The pointer is null, so we create a new node
null.
there.
So instead of a null, I'll create a new node. At this point, I allocate a new word, a new node. What is the word that this node corresponds to? It corresponds to DA. The label of this edge is A. So the string of this word is DA. The reason that I'm making this deal with labels of the edges is because otherwise you start to get confused. Do I actually take the letter that this arrow points to, which is meaningless because it always points to the beginning of the word, or do I take, it's much simpler to think about labels of the edges and concatenate the edges because it's clear what is the edges. It's not clear when you look at the nodes, what are the letters from the nodes that you are collecting. So trust me, it's simpler. Okay, I created this node that is DA, corresponds to the word DA. What is its flag?
0.
0. DA is not the word that I'm inserting. And go ahead.
We see that A also points, has a null pointer, so we create a new node.
And create one new node. Also comes from A. This word corresponds to DAA, and its pointer, its flag finally is 1 because it's a word that I just inserted. How much time did it take? The length of the word. But you see that inserting one node might imply a lot of new nodes that are created. So one insertion might create a lot of words. And the reverse operation is almost obvious. Before I'm getting to it, before deleting, let's insert one more word. Insert of DA. Somebody else? Insert
this
DA.
one, when you just start with D, which is not null, so you go D, and then you can go to A, and that exists, and then you just set the flag to 1.
Yes, excellent. D, and this flag that used to be 0 is now becoming 1. Excellent. Now, to delete a node, first find it, say DAA. Next, change its flag to 0. If I want to now delete DAA, I'll change its flag to 0. And now I have two options up to me. If I am not short of memory, then I can stop the operation right here. There is nothing wrong with stop the deletion right here. If I do want to be conservative with memory, then I'll check this node carefully. I'll say all its pointers are null. Its flag is 0, so it doesn't give me any more information, so I can eliminate it, which would possibly cause me to eliminate its parent, and possibly cause me to eliminate its parent, and so on. So the same cascading operation that we did in the insertion, that one insertion caused a lot of words to be created, all these words might be eliminated when I'm doing it in the opposite direction. Okay, so fantastic data structure, really efficient. We will see today or tomorrow a geometric relative of the trie that essentially the 4 letters A, B, C, D corresponds to different portions of regions in geometric domain, like different squares. It's data structure called quadtrees that shares a lot of the properties with tries. At the moment, the only bad thing that we can say about the tries is it uses dynamic memory allocation, which, as I mentioned many times, if I need to create linked list, I need to put new words. I don't know where this new word will be allocated in the memory. There are some processes that might try to optimize it, but it might be actually in memory quite far from the rest of the world. So operations like caching or moving things to the disk and from the disk, paging, might be affected. Memory allocation is, in general, something that if you can avoid, it's better. Your compilers will work better. Your optimizer will work better. Parallelization of your code will work better if you use static array. Static array says you tell the operating system, I need an array of size 3,000 bytes, and that's it. You declare what the size that you need, and you're getting a contiguous source of memory right there, and that's as efficient as it can be. But so it's one disadvantage of the trie comparing to, say, open addressing hashing. And open addressing hashing, for the same reason, by the way, is much better than chain hashing, because chain hashing, when every cell of the hash is pointing to a tree or pointing to a linked list, use dynamic memory allocation once again. The same operations that we prefer to avoid if possible. At the same time, trie has lots of great things that work for it, and it's very, very practical data structure. Lots of applications. Inserting a word is as fast as possible. Just order of the number of letters of the word. Word is short, it's constant time. I don't care at all how many other nodes there are in the trie. But there is no log n or something that depends on how large your database is. The running time depends only on the length of the new word that is inserted. Okay, what happens if my alphabet starts to become larger and larger? For example, I have all the small letters of the English alphabet, or all the ASCII characters. Then each node, remember, each node should contain, besides the flag, one cell per every letter in the alphabet. So what is the worst case space requirements that I might need? It will be how many words, that's the naive bound, but how many words do I have in my alphabet? How many students do I have in my class? That's the size of S. And for each one, at least, I need the leaf for it. So it's times sigma. Sigma by itself is a length. Sigma is the alphabet. Sigma with bars on the side is how many letters do you have. So that's how much do you need per That's a memory requirement for one node, and you need at least these many nodes, possibly many more. So the space requirement might be an issue. So what happens if my alphabet is quite large, lot of letters? Remember, every node is an array with lots of fields. There are a few heuristics that you might consider using, but every heuristic that I'll mention also has a penalty coming from it, that it makes your code in a sense slower, because now you have more decisions to make. The debugging has more to worry about. So heuristics means that all this absolute simplicity that we saw for the insert, delete, find operation for the try, if I'm using the heuristics, now they are less simple. I need to work much harder on my code. But if I'm worried about my memory, my first heuristic is the following. I said that in the word, in the node, I don't need to store the letters that a cell corresponds to. Again, if the cell that corresponds to A will be the first cell. The cell that corresponds to B will be the second one, and so on. From the location of the cell, I know what is the letter that it corresponds to, and vice versa. A very possible heuristic, if you know that a node, when are you wasting a lot of memory? When will you all cry out from frustration, this is such a wasteful structure? If my root has all 22 or so, or for children are live nodes, live pointers, then it makes sense to store the root as is, if all or most of its cells are live pointers. When does it start to be really frustrating? Can you guys tell me how to insert the word A? What will it look like in this tree? I erased some of the tree, but that's fine. What will it look like? When I'm inserting the letter A, the word A. It's not hard. You are performing the insert operation for this word, and you realize that this pointer, we had actually an A beforehand, doesn't matter. Here is the first letter of A, here is the next letter of A. These are all pointers coming from A. Next one, and so on. I have a lot of nodes where each node has only one child, or two children, or three children, but there is a lot and lot of empty, wasted memory in each one of these nodes, and there are many of them. Again, each one of these nodes, almost all the cells are pointing to null, or empty, they are waste of memory, and there are a lot of nodes along this shred. So you're wasting a lot of memory for one single word. And it's not that frustrating if your alphabet only consists of A, B, C, D. It's more frustrating if your alphabet start contain many other symbols. 20 if it's amino acids. 22, 6, something. If in English also, 20 something, right? Do I want to ask the next question of what will be the size if I were using Mandarin? Probably arrays will be quite wasteful. Lots of empty cells per each node. Very wasteful if you want a node that have a cell for every letter of your alphabet. So there is a simple heuristic that we will not prove anything about it, but definitely you can use. It will say I need two types of nodes now. I'll introduce one new type of nodes in addition to the old type. And the new type of nodes will be more economical in the case that a node just have one child or two child or three child at most. If it has 4 children, then I'll use a traditional node structure. So first, as you know from C, if you are using a struct, two types of struct that might overlap with each other, the first byte must tell you which type of struct are you using. Is it a traditional node or is it the new compact representation? So the first cell of my new node will tell me what type is this, traditional or the new heuristic. And if it's from the new type, then instead of storing all the letters from A all the way to Z, I will store only 3 pointers, at most 3 pointers, maybe only 2, maybe 1. But in this case, I don't know I lose the locus of knowing from the location of the cell to which letter it corresponds to. So I need to store what type or what is the letter that it corresponds to. Meaning that, I think that one example will simplify it. In the case of A to Z that we had before, let's say that only C and K are the only non-null pointers, only C and K, and everything else is null. And this will be the old type, type 1, then type 2 node, a compact representation, since I have so many empty cells over here, then type 2 representation will say store C explicitly in the node, and after the C, store the pointer that the C corresponds to. Store the K explicitly in the cell. Remember, type 1, I don't need to store that it's coming from K. I know that it's coming from K based on its location. Type 2 will say, no, we will actually store what is this K, and then the next cell will be this pointer, the same pointer that this guy was pointing to, and maybe you'll have one room for another word of this type. Okay, so you'll use the new type if a node has at most 3 children, and if it has 4 children, then use the old type. 3 and 4 is arbitrary, you'll pick your favorite constants. Okay, that's just the heuristics. But of course now, when you're doing find or insert or delete, you first, when you reach a node, you first check, is it from the old type or the new type? Because the new type is much shorter in memory, it covers now much shorter place, but I need to know how to understand the bits in the new structure, how to break them into fields. And C is built to give you the nice tool to say this struct might be of this type or of this type. That by itself doesn't tell you much. Again, another example, you have letters only to B, only to F, and only to R, only 3 nodes. Store the B and F and R with exactly this node. Just forgot that I have a slide for it. You actually can. The next heuristic is much more powerful. The next heuristic that I'm going to show you, meaning that it stopped being a heuristic. I want you again to think about this shred and how frustrating it is. So a shred will be a sequence of cells, each one has only one child. Notice it might be that the last cell over here has 2 pointers, or 3 or 4 coming from it. So I'm less frustrated with the last pointer. From this pointer, it will not be part of the wasteful part. The wasteful part that frustrates me so much is what's encapsulated right here. Sequence of cells, each one has only one child. sequence of cells have only one child. So we think about it as a path of a shred. There is a sequence of cells. It might start at the root, not necessarily. It might end at the leaf, not necessarily. It might be end at internal node. But a path will be a sequence of nodes. All of them contains only one child, excluding maybe the last one. The last one might contain more than one child. So, and in my tree altogether, in my tribe, I might have a lot of such paths. And they start to be dominant only if I have a really long shred and then a long such shred, a path, and of course when the alphabet is large. For 4 letters probably doesn't force the troubles. If the number of letters starts increasing, then each such area is, again, it's frustrating because it's almost completely empty except of one pointer. So what am I doing with such a long path? I will using a new heuristic called path compression. What is path compression? I realize that there is such a path sequence of nodes, each one points to the next one, each one has only single child, and I'll replace it with a new type of node. This is the cell types that we see. We had the traditional one, then we had the one that has only 3 nodes coming from it. This is the cell type of node. How much memory do I need to store the sequence B, 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 B? I need to store it by wasting just 1 character per each letter. I need to waste only 1 character per each letter. That's a minimum that I can do. On the other hand, here is a long sequence of node B, 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 but for each letter I'm wasting the whole huge array. How about taking this whole path and just say, here is my new type of node that will replace this whole path. Well, this node has 2 pointers coming from it. The lowermost node of this path has 2 or more pointers to it. So what happened to the new node that replaces this whole path? It will store a pointer, say, here is a pointer from B. This pointer from B points to here. I'll replace it by a pointer from B that points to right here, the same place. Here is a pointer from C that points to some other place of the tree, or to a real node. There will be a pointer from C actually, that points to the same row, so you still have it. But what's new about this cell type of node is that they can store a string. And the length of the string is unlimited. As we'll see when we get to the next application, there could be a really, really, really long string stored here. And it's an example, just an example here that all the letter in this case is the same. It doesn't have to be. It could be ABC, ABC, ABC. But it's just a string that I stored in the node. Here in this example, for Freudian reasons, again, I used A, same letter again multiple times. I will place it all with a string on this part, including the last one. Including the last one will be replaced with a string that contains, this whole thing is replaced by a string that somewhere along this string I will store A, this A that you saw over here, and of course the same pointer that points to, say, that points to A, this guy that points to the same place that that the A in the old thread works, and a new node, let's use green, that points to B. And the same depending on what the last node of this path will correspond to. Because the last node of such a path might have no children, might have 1 child, might have 22 children. children. I don't care. It's all its ancestors that I'm frustrated with, and I'm replacing all of them by just one single path. Okay, so what is the size of such a node? You don't know ahead of time. It depends on what the string that you're storing here. If you're replacing in this compact path a very long string, then this node will be quite large. So again, you're using dynamic memory allocation. And let's see one more example where we can use this trick. It could be that this node was already a leaf, and then it doesn't have any children. But it could be that my tree has a few paths on the same, a few paths that I need to compress on the same path. Let's take the letters A, D, and here I'll have A, and another A. Yeah, I have some obsession with A, over here. So let's identify in this string how many paths do you see that you can compress in this string? Try 3. How many new created nodes are you going to generate? That's my original tree, all uses only traditional nodes, and I want to use this next heuristic, the path compression heuristic. And I'm asking you, after path compression operation, how many new compressed nodes are you going to generate in this tree?
We could compress it into 3 nodes?
Yes, 3 nodes. That's the correct answer. So my new tree will look like, my new tree will consist of, let's compress everything here. So my new tree contains a string of, I need to write it probably larger, a string that will have A right here, and this string replaces everything that you saw over here. If we write this A once again, it will correspond to A once here, and then I have what happened to the end of the string, to this guy. It has a pointer from the A field. It has a pointer, its B field points to null, C field points to null, and D field points to, and now what are these 2 nodes points to? Originally, we think about them as they point to where this A is pointing to, right? And the D will point to this guy. But here there is another path that I can compress. I can compress everything here into a single node, everything here into a single node. Right. So I'll just draw one of them. Here is another path that replaces all, let's call this path 3. So path 3 will be what this node will correspond to. That will be, well, I just used A over here, so it's A, once again, and what happened to all its, what are its ABCD cells points to. Look at this guy, it's a leaf, meaning it doesn't have any children, all its children are null, so everything here will point to null. Okay. So when you allocate, when you are using the new command, you are asking, here is the length of the string that I'm going to stack into it. And how does your computer, your program knows that you got to the end of the string? It has a backslash 0, that is how C knows that you got to the length of the string. So to make it all useful, you're using it if you have such long path with only one child. Long path if they have only one child, and you replace it all by one node. So I want to re-explain where the saving here in the usage of try. We will see the path compression coming up, and it will be much more powerful in one more application. But at the moment, even if I just use it for normal tries, what is a big saving up coming from? You have a lot of nodes here. Each one is quite large by itself. It's traditional node, so it has at least sigma many cells. Each one, or only one of these cells are used. So to store this 1A over here, you're wasting, to store this one pointer over here, you're wasting a whole big array of the whole alphabet. To store this A, you're wasting the whole alphabet. Wasting the whole alphabet in each one of these nodes. So instead, you are replacing it by storing only a single letter in the string, in the compressed node. So this is path compression. Okay. So but as you know, no free meals, no free lunches. What you're saving memory, but in return your program is less and less simple. Because now when you're following a path, either in order to insert or to find or to delete somebody, you have to check for each node which type are you, and each type is treated differently. But do think when I'm checking, if I want to now check if the word find of, well, I'll do it shortly, A, D, A. So it's A, D, here in the middle, and another A, to ask if it is in my try. It is if there is a student with this name in my class or not. I need to start from the root, realize that my first node is a compressed one, stored, progress along the string that the compressed one, the string that the compressed one contains, that covers all this part, get to the end of it, see that the D is not null, go again into a compressed node and check if this compressed node, this compressed node over here fits exactly this word, and so on. So you, meaning that as you're doing the find or insert or delete in the new try with all the heuristics, now every time as you're going down the tree, you might switch from one type of node to another one, and you realize that you always have to concatenate whatever the word that you are generating, but each time you need to ask to which type of node it is, and are you getting just one character or multiple characters from this word. Okay, so we saw that tries are very nice in order to just store a lot of words. Again, probably if that was the only applications, there are advantages to, if I only need to insert, delete, find. Maybe hashing will do better, but try supports a few other operations, and they definitely give a good competition to hashing. And as we said, they are optimal in many senses. But they need a lot of memory, obviously. Okay, next application. So when you look at, hopefully among you guys, I hope that most of you know, and if not, then you should know that VI is the best word processing in the world. That whatever you are using, just use VI or Mac VI or VIM, and you should do all of it. If you like Emacs, you're in the wrong class. You know, humanity divide between Emacs and VI. But I think definitely in VI, I think that probably in most other worlds, in most other editors, you can perform find of a word. That is, you'll type hello, and it will take you in the big file. It will take you to where the word hello appears, if it appears. That's for normal find. But you can also do incremental search. I think in VI it's called incremental search. You might know it in different terms. If yes, then please let me know. That will say, I want to type the word hello, and if you're doing normal find, you type the word hello, click return, and the cursor will move to where the word hello appears. If you're doing incremental search, then your cursor stands somewhere, say at the beginning of the file, and you're typing age, and the cursor will jump to the first appearance of age in the file. And then you're typing the E of the hello, and your cursor will jump not to the first E of the file, but your search knows that you typed so far HE, so it will take you to the first appearance of HE, if you have it in the file. Type the L, you'll jump to the first appearance of HEL in the file, and so on until you're done with the hello. But everybody has experienced it in some way or another. The same way that when you type in Google the web address of something, as you are typing, it tries to guess what do you mean as a suffix, or how should it autocomplete the word that you just started typing. And I know that there are multiple solutions, and sometimes a commercial property of how exactly these algorithms work, but I want to suggest to tell you at least how some of them works. So my problem right now will be a bit different. My problem will be that somebody gave me a very long text. I call this very long text B, a book. Very, very long text, all more above the alphabet that I'm using. And I want to take this big book B and pre-process it, that is, meditate on it, prepare a data structure that fits it very well. Hopefully this data structure that I'm going to prepare is not too large, such that when I'll type hello, the word W, I will find quickly if W is in the book, and if yes, I want to know where in the book it is. Okay, take me to the page that contains the word hello. Make sense? And I want to tell you how to do it. Now, W is not necessarily the prefix of a try. But try already sounds somehow familiar, because let's go back for the image of the try for a moment. Let's go to for the try for a moment, and I'll ask you, look at this try and tell me, is the word is the word B a prefix of any word in S? So a prefix, we played a lot with prefixes when we studied LCS and edit distance. Another prefix might be that either any DB is a word in S by itself, or that there is a word in S. Yes, in this example, the word DBB is in S, belong to S, and the word DB that I wrote right here, DB is a prefix of this word DBB. So the answer should be yes, and it's very easy from the try to find out if a query word is a prefix of any word in S, right? How would you do it? You're just going to the root and pretending that you are performing find operation. So the find operation will take you all the way into this node. And if you are careful that every leaf, every node is alive only if it has live children or live descendants, word that has one in its flag, then if this node exists, the node that fits the prefix exists, then it means that there is somewhere a word in S that at least starts, that the search will take you all the way to here and maybe continue. Maybe this word is DBB in this case. So it's very easy from the try to find out if a given word is a prefix of any word in S, right? Which hashing will be less convenient to do. If you do hashing and try to answer the same query, you'll have to work much harder because you have now to hash every possible ending of this prefix that I just wrote. Back to our book. Everybody understood what I meant about performing queries of a prefix query? Let's call this thing a prefix query. People on Zoom, it's clear how the try helps me perform a prefix query in the example of a normal try. Example of multiple names of students in the university is a given word is a prefix of any name of somebody at the university. Just look for it in the try. Back to my book. I have this book, it's huge, terabytes and terabytes of data, all alphabetic beta, all alphabetic strings. I want to preprocess it so that when I give you a word W, you tell me if W appears anywhere in this book. I want to appear to know if W is anywhere in this book. So imagine that this book B is A, F, A, G, H, E, F, O, D, Q, R, S. Here is my book, and I want to ask for the word W. Is the word hello? Does it appear anywhere inside this very long book? And what's the observations that you want to make? You want to think about B as a very long string and make the following observation. W appears as a word somewhere in the book. W, hello, appeared somewhere in the book if and only if I really enjoy saying the next sentence, it's a nice tongue checker. Say this word, say the sentence quickly. W appears somewhere in the book if and only if W is a prefix of some suffix of the book. W as a string is a prefix of a suffix of the book. What is a suffix? Prefix, you all know, hopefully. You are all, if you paid attention when we talked about LCS, you know what are prefixes, what are suffixes. Look at a word, and the suffix of this word will be either the last letter, or the last two letters, or the last three letters, or the last four letters, or the last five letters, or the last 0 letters. The empty one is also a suffix. Right? you are not reversing the order. Don't get confused with changing the order. The order is the same. I read it still from left to right. But the suffix means takes only the few characters at the end of the word, or alternatively delete a few characters from the beginning of the word. So the suffixes of A, B, of A, B, all the suffixes are here. Now, let's think about my observation. W appears somewhere in the book if and only if W is a prefix of a suffix of the book. It should be, think about it, and after you think about it hard and heavy for 2 months, you realize that it's absolutely trivial. Why? Because hello appears over here, either a suffix that contains the word hello as a prefix, either a suffix of this book that contains the word hello. How do I get a suffix? I need to delete somewhere at the beginning. That will create a suffix of the book, and hello is a prefix of what is left after the first deletion. Right? A proof by example. Hello appeared because hello is a prefix of the string HELLO DQRS, and the string that you see right here is a suffix of the whole book. Everybody buys this observation? W is somewhere on the book if and only if W is a prefix of a suffix of the book. I love saying it. It means you can take the whole book, delete somewhere. You are asking, is hello appears anywhere in the book? Yes, it will appear somewhere in the book consecutively. We are not in a substring business anymore, or subsequences. Consecutively, it appears in the book. If you can go to the beginning of the book, delete something, then go to the end of whatever is left, delete something, and you'll be left only with the word W, with the hello. So if everybody agrees about it, and hopefully everybody agrees that tries are really good in finding if a prefix exists in the list of words in the dictionary, now we are start to introduce the idea of a suffix tree. So there is a clear confusion. I mean, I've taught this topic billions of times. There is a clear confusion. We have tries, and I'm going to use tries in order to create suffix trees. I'm not creating suffix twice. I'm going to create suffix trees, but suffix trees will create twice. And the usage are different. Tries are working for a set of different words. Tries are working for a set of different words. We're writing it. Tries solves insert, delete, find in a collection of words. Words, with a lot of words, and suffix trees use tries to pre-process a large book so we can efficiently find query words in the book. That's how trees and suffix tries are going to work together. So finally, what is the big algorithm that I'm going to suggest? What's the implication of this great idea? So if W, you ask me, is W in the book? I need to ask, is W a prefix or some suffix in the book? So what is the idea? Twice likes to take a set of words. What will be my set of words? I'll think about the book, this very long text, as a very long string, and now I'll create a try T. What are the words with plural that I'm going to put into the try? They are going to be all the suffixes of B. So you're inserting n suffixes into B. Quick example, here is my book, A, B, A, B. Let's create all the suffixes of B. These suffixes will be just B, this B at the end, or AB, the two letters at the end, or BAB, these three letters, or ABAB, these four, or just the whole words, the whole book. These are all the suffixes of this book. Start from an empty try and insert the word B into this try. How would you insert it? You start from an empty node. You are trying to insert the same algorithms we studied, create this new guy here, because you are trying to follow the B cells coming from here. This B used to be null, so we are creating one new node for just inserting B, making this one node has a flag of 1. And actually, I'll store over here also where the suffix appeared in the book. There is some auxiliary data that you need to store there. And continue. Now I'm inserting A, B, and the next suffix. A, sorry, B. My figure should have been here on this node. You're trying to insert it, it doesn't exist, so create new nodes, just the same insertion as before. Make sense? And in this way, you're creating all the suffixes, create all the suffixes, insert all of them into the try, and now when I ask you, is the word ABA, is ABA appears in the book or not? Is ABA appear in the book or not? The answer is, if it appears, then it must be a prefix or a suffix that I saw over here, right? And indeed, BAB appears as a prefix somewhere here. And how do I find it efficiently? I'm performing, you told me find if B, what did I say? Sorry, ABA. I mean, find ABA. ABA is a prefix of a suffix of the book. ABA is a prefix of the string. This ABAB was inserted, ABAB was inserted. I don't care that there is a 1 over here. I do care that when you told me to look for ABA, look for ABA, ABA, it exists. I reached to some nodes. Don't care what's written right here at the moment, meaning ABA is indeed appeared somewhere in my book. ABA appeared somewhere in the book because it's a prefix of a suffix. So it looks like I almost solved the problem. I let you work in the homework about what extra information do you need over here to tell me not only if ABA appears in the book, but also to tell me where it appears. My cursor should jump to this point. So it's a great solution as long as you don't care about what's wrong with this. But just screaming out wasteful. Zoom, guys. Let's say that the book is very, very large. all the all the all the legal texts created ever in Arizona. So the book is very large. But okay, you need to store the book somewhere in your memory. It's not more than whatever, many terabytes that you can indicate. But what is the total length of all the suffixes? Of all the suffixes that I'm going to create? N square, right? It's 1, there was a suffix of size 1, plus 2, plus 3, plus 4, plus dot, 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 n, which is theta of n squared. And for each one of them, I need to create a pretty large array that might store it. So it's n squared times the size of the array. So far, everything is fantastic with the try beside its memory. You're going to use the total length of all the suffixes, the number of nodes that you're going to create might be as bad as n squared. If your book is terabyte long, then terabyte square is lots of memory. So we need some trick that will help us compress the tree outer. And here comes a really beautiful, beautiful piece of theory, very simple graph theory, that will convince us that this book is actually very practical. So the algorithm is going to go as follows. When we are building the suffix tree, we first building it explicitly and wasting the n squared memories that you might need. Okay, so temporarily you'll build the book, but without any heuristics. All the nodes are traditional nodes with all the alphabet. So the memory is quite wasteful, but it's only temporarily. Now I'm going to go into this book and perform the path compression heuristics. The second heuristic that I was talking about, that's what I'm going to perform on this book. And this plus one more trick will be enough to tell you that I can, so to go over it is build the suffix tree explicitly. It's not how you spell explicitly, but you understand. And now use path compression plus one very, very simple trick that we are going to use in this path compression. And this part will take theta of n squared memory. This part will take theta of n squared memory. So temporarily you'll need a lot of memory. But why do you need this whole data structure? You're not just using it once. You want to be able to go through your library of legal text and once in a while to do search for a word. There is something that you are storing all the time. So this something that is stored all the time after the pre-processing, I want it to be much smaller. So what I'll convince you to know is that after this path compression, plus two more tricks, one more trick, the memory is down to linear, theta of n. N is the number of words in the book. You are storing the book no matter what. So with the penalty of storing this book times only a constant, but very, very far from n squared, I'll be able to have this fantastic data structure that takes a word anywhere in the book and will take me exactly to this word. And by the way, the search that I'll do, because it's a suffix to convince yourself, we talked about incremental search. Right? I start to type hello, or I start to type ABA, then when I type the A, it will take me to here. When I type the B, it will take me to here. When I type the ABA, it will take me to here. And if this node knows where ABA appears in the book, then I can already, at each point, jump to the right place. So there is one very simple argument about graphs, about trees that I'm going to show you. Trees as graphs. And that will convince you that path compression makes this tree very dietetic, very slim. You'll only need linear memory for it instead of z-square. Okay, so that's for tomorrow. And then the next week we'll talk about human fine and Kruskal algorithm. That might be our last topic. Maybe we'll have just a bit more time. Only cute things from now until the closing end of the course. Any questions? People, Zoom, again, homework 5, all good? Okay, thanks everybody.